So first, let's review what we learned last time. Last time we talked about the periodic trend, which is based on, if you're just based on the periodic table, how can you predict some of the parameters for atoms? First of all, like the atomic size. The atomic size, the trends. And once again, the atomic size is talking about the size of the electron cloud, which is we have the cloud, the electrons is in outside. The size of the electron cloud it generally is talking about the atomic size. It's not talking about the size inside of the nucleus. The overall trends is on the top right parts, we are having really small atomic size, but in the bottom parts, we have a biggest atomic size. They are from top to low, we have from smaller to bigger, from right to the left is also smaller to the bigger. But those are atomic size usually is not including the noble gas, because noble gas usually is bigger than the fluorine gas. So if you're talking about smallest size, that probably is fluorine. Okay, fluorine is the smallest. Or helium. Helium is the smallest size. Okay, and then we also talk about the size for those metal and its cations. Usually metal is bigger than the cations because they lose the cation losing one of the shell. So definitely the metal is bigger than that. For the non-metal, usually the non-metal, the size is smaller than their anions. Because when they receive one of the charge or receive the electrons, they are going to become a noble gas electron configuration. And we talk about if they're fully packed with the electrons, and then the size usually is bigger than other elements. We also talk about the size, how to compare the size for isoelectronics. Isoelectronics, okay, is talking about the one has the same electrons, okay? So those a group of elements or ions, they are having their isoelectronics because all of those guys has the same number of electrons. They all have 10 electrons, okay? Although they have the different protons, but they're going to have the same electrons. Those are called the isoelectronics. How to compare the size for the isoelectronics? You just need to look at which one has the biggest protons. Aluminum has the bigger proton than the rest of others, so the aluminum is the smallest one. The one has the bigger proton, then they are going to have a smaller size. Okay, so this is a comparison between the isoelectronics. And we also talk about the ionization energy. Is talking about how much energy required to remove an electrons. Some of the elements already like to remove electrons. Some of this not like to. So the ionization energy will be different. The general trends is the top parts is the largest and the bottom part is smallest. So those part, which is the fluorine, has a really high electron ionization energy. Neon has even more ionization energy. So the neon, helium is the smallest and has the highest ionization energy in this case. Then we also talk about the electron affinity, which is talk about which one like electrons. If you give one electrons to these elements, which one will give you more energies? Okay, which one will give you more energies? So in this case, still the same trends. Still the top right parts like gain the electrons. Bottom left don't like gain the electrons. And this trend is not including the neons, the noble gas. Probably start from here because this guy is the most one like the electrons. Neon don't like electrons. They have a packed electrons, so they don't need. Electron activity is talk about which one will have. If you have two atoms of there, which one will pull the middle electrons to? Okay, which one shows bigger muscles? Okay, yeah. If you're the one on the right side has a bigger electron activity, then the electron will pull into the right side. If the left one has the higher electron activity, then they're going to pull into the left side. That's it. Okay, so and we also talk about valence electrons. This is this is also what we talk today. It also is a follow-up for this one. This is called the valence electrons. Valence electrons talk about how many electrons in the outermost shell. The outermost shell, which means is the shell in the very outside. So once you have write down the valence electrons, write down the electron configuration, you just need to look at the biggest number shell and then count how many number of electrons there. That's it. Okay. Or the other way, you just need to look at the group numbers because valence electrons is the same just like group number. But here, this group number is only for A group. It's only for A group. It's not for the others. Okay. A group, the number of the group number is the valence electrons. Okay. And here we're only talking about the valence, the A group, the valence electrons. Okay. So generally, this is pretty much what we talk about in the last class. Okay. Okay, so now we're going to talk about the Lewis structures. The Lewis structure is a formula, but that's called a structure formula, which means it also shows the relationship between each of the atoms inside of the molecules. They talk about which molecules will have a bonds between each others. Okay, so for the Lewis structure, there are several differences. Okay, so first one, let's just talk about the single elements. If we only have a single elements, how to write the Lewis structure for single elements? For example, aluminum. Okay, if you want to draw the Lewis structure for aluminum atoms, then you need to know what is the valence electrons for aluminum. Okay, so you first need to know what is the valence electron for aluminum. What is the valence electron? This guy is in the 3A group, right? Aluminum is in the 3A. So group number is 3. So this guy valence electrons should be 3. They have 3 valence electrons. Okay, we talk about how many number of the electrons they're going to have. This guy is a 3A. So aluminum has 3 valence electrons. Their group numbers is equal to the valence electrons. Okay, so they have 3 valence electrons, which means we need to assign 3 dots in the outside of the aluminum. 3 dots in the outside. So for elements only, what we gotta do? We need to assign single dots on one side. Aluminum, I mean, each of the elements has 4 sides. Okay, they have 4 sides. So we need to assign one single dot on each side first. Since we only have 3, so you assign 1, 2, 3. Then that's it. Okay, so assign one single dot on each side first. So this is the rule. You can write like this, aluminum. You can also write like this. Or you write like this. That really doesn't matter, okay? As long as you assign one single dot on each side, then that's gonna be great. Okay, so it doesn't matter. But this is not right. If you write like this, that's not right. If you write like this, that's also not right. Okay, yeah, one single dot on each side first. So this is aluminum. So how about carbon? If you look at here, carbon is a 4A group. So the valence electrons is 4. So if you're assigned the dots, you're gonna assign 4 dots around the carbon, which means you're assigned, first you're gonna assign each of the dots on one side first. So this is the carbon. Okay, how about the nitrogen? Nitrogen is a 5A group, so the valence electron is 5. So you're going to assign single dots on each side first, but the point is they have 5. So you assign 4 dots. Now you need to assign 1 dot, and this 1 dot will appear with the previous dots. Okay, so that means your one of the side should have a paired dots. The rest of the other side, the 3 sides, will have a single dots. That makes sense, right? So the paired dots doesn't matter where you put the paired dots. You can put it over here. That's fine. You can put it over here. That's fine. You can put it over here. That's fine. Or even you put it over here. That's fine. Okay. So doesn't matter where you put the dots, as long as you need to make sure first you assign single dots on each side. And if you have more, you're gonna pair the single dots to a paired dots. Okay, yeah. So this is for the single elements. Very, very important. I'm going to emphasize this is only for single elements. If you have a compound, then that's a different story. Okay, so when we talk about this compound, we're having some of the name calling this. So this is called paired electrons. Or people also call this is called a lone pair. It's called the electron lone pair. Why is called the lone pair? That means usually when the electron pair together, they are not going to have any of the chemical reactions related. So this paired electrons will not involving any of the reactions. So it's just lonely sitting over there, nothing, do nothing. So that's called a lone pair. Okay, electron lone pair. Okay, so this is for the single elements. Then let's talk about how about the Lewis structure? For ionic compound. Lewis structure for ionic compound. So for the ionic compound, for example, the sodium and the chloride. If you just draw the Lewis structure for sodium, then you know sodium is 1A group. So they are going to have just one dot. So this is the Lewis structure for sodium metals. And if you're talking about the chlorine, chlorine atoms, they have a 7A group. So you're going to have 7 dots around it. So you have 3 lone pairs and 1 single dot. So one day the sodium and chlorine meet together. The chlorine said, "Hey, sodium, I need your dots." Sodium said, "Sodium's so weak. Okay, I gave to you." Okay, so what happened? The sodium is completely losing the dots. And this dot is completely be gained by chlorine. Sodium is completely losing the dots, and the chlorine is completely gained the dots. So since the sodium, they losing 1 electrons. So they become a positive charge. A chlorine gain the electrons. So once you draw the Lewis structure for chlorine ion, is not like this. The chlorine is not just the gain electrons. Instead of beside gain the electrons, the chlorine also gain 1 negative charge. Okay, so when you draw the 8 dots around the chlorine, and meanwhile, you need to have a negative charge for the chlorine. This is very important. And by the way, a lot of people confuse why we need to write a bracket. Why this one don't have a bracket? Chlorine here, they are having a bracket. Is the major thing is try to separate the charge and the dots. Okay. Remember, this method developed in like a really long ago. At that time, there's no computer, no printer, okay? So everything is handwriting. If some of the scientists has really bad handwriting, and they put the dots and the charge all together, and it's really hard for you to identify, is it the charge or just the dots, okay? So that's why they said, if you have the elements that has the dots around it, you have to have the bracket to separate the charge and the dots. Okay, and why sodium don't have to have a bracket? Well, is there any dots around it? No, right? There's no dots around the sodium, so you don't have to write a bracket. But if there do have a dots around it, then you need to have a bracket to separate the charge and the dots. Are you clear? Okay. Okay, so when the sodium and the chloride combine together, making a sodium chloride, that is the Lewis structure for sodium chloride ion. Sodium chloride, the compound. The whole things here will be just the Lewis structure for the ionic compound, sodium chloride. Okay, they have a sodium ion and a chloride ion. So eventually, the Lewis structure shows so inside of the compounds. This is made by cations and anions all together. Okay. And if you're talking about like a sodium oxide, how to write the Lewis structure for sodium oxide? Since we have a oxygen has a 2 negative charge and sodium is 1 plus charge. Then how do we write like this? Sodium still, they are going to losing 1 electrons, and oxygen originally is like this, right? So this is oxygen. They have 6 electrons. Okay, they have 6 valence electrons. So you have to write like something like that. Okay, so this dots, we have 2 sodiums, and each sodium have 1 single dot. The very interesting thing is, okay, so they prefer those elements if they have a single dot, and this single dot is very, very active. Okay, they try to be paired. Okay, they try to be paired. I'm not sure whether you're actively finding your pairs, but the electrons is actively finding their pairs. So they are having, if they have the single dots, they're going to actively finding pairs to make a lone pairs. Okay, so this dots is going to giving to the oxygen over here to making a pair, and this dots is also going to making to here to making another pairs. So those oxygen will be have 8 electrons and they fully packed. So that's why they're going to become a Lewis structure. The oxygen in the center have 8 electrons in the valence electrons in the outside. And in this case, oxygen has a 2 negative charge, and sodium, they're losing 1 electrons. This sodium also losing 1 electrons. So that's gonna be the Lewis structure for sodium oxide. That's gonna be the Lewis structure for sodium oxide. Are you clear? All right. So the next part we're going to talk about the Lewis structure for molecular compound. Lewis structure for molecular compound. So first off, let's see what happens when the molecular compounds have. For example, so we have 2 hydrogen over there. So one day the 2 hydrogen meet together, and then this hydrogen said, hey bro, can I have your 1 dots so I can have a pair of dots, then I'm stable. And this hydrogen says, no, I'm not going to give your dots. I need a 1 dots too to become a stable too. So they two are gonna fight together. I mean, none of them, since they're identical, so they cannot, none of them can have the dots from the other one. So, but the point is, everyone needs stable. So what happens? So they sit down and then think about, okay, so now you're not going to give me dots, and I cannot have the dots from you. And I cannot give you my dots. So how about we're making a deal? Okay, you're going to share your dots, and I'm going to share my dots. So we have 2 shared dots over here. And this dots is no more belong to you, and is now no more belong to me, is belong to us. So this is what happened for the electrons, for the molecular compounds. They're not going to completely gain the electrons or losing the electrons, because nobody can do so. Okay. Instead, they're sharing the electrons to make them to shared. So those two dots is not going to be gain to each of the side. Instead, they're going to share in the middle. So these electrons belong to the one on the right side, left side, and also is belong to the right side. This air is a shared area. Okay, so this hydrogen is shared. This hydrogen, those two dots is shared. Okay, instead of, so that's why say this is the complete difference between molecular compound and ionic compound. Ionic compound, sodium ion, the dots, the electrons is completely loose. And then the chlorine is completely gain the dots. Then both of them will have a charge. One has a positive charge, one has a negative charge. But for the Lewis structure, for the molecular compound, none of them have a charge because they are sharing the electrons. This electrons is belong to both of them. Okay, so none of them have a charge. That is very, very important. So that is why you can think about the sharing is the very, very good attitude. Okay, think about how much do you share the things with your siblings? No. I don't have a sibling, so I don't have to mind. Okay. All right, so this is the Lewis structure. So the people, if you have the shared electrons, then the shared electrons become rewrite as a dash. And this dash is a bond. It's a bond between each of the elements. Okay, so it's a bond between the elements. Okay, and this bonds is called a single bonds. This bond is single bonds. Some of the cases, like oxygen, the two oxygen will do the same thing. You see, each of the oxygen would like to share one electrons. So we have two single electrons on each of the oxygen. So they would like to have two shares. Okay, right? They have two shares. So that's why those two shared two dots are all shared in the middle. So now instead of we have a one paired shared, we have a two paired shared now. Okay, so the two paired shared electrons become double bonds. The two pairs of the shared electrons will become a double bonds. One pair becomes single bond. Two pairs become double bonds. And also we have one called the triple bonds. So if you're looking at the nitrogen, then you will see nitrogen has 5 electrons, and they have 3 single dots over here. Each of them has 3 single dots. So they said, why do we just share, everyone offer 3 electrons, so we have 3 electrons be shared. So now they are sharing 3 electrons altogether. Okay, so the 3 pairs of electrons making it a triple bonds. And remember, the shared electrons will rewrite as a bond, but for the rest of the other dots, you still need to keep there. Okay, you still need to keep there. So in this case, we still have lone pairs over here, and we also has a lone pairs over here, and then we're writing the 3 pairs of the shared electron become a triple bonds. So this is called a triple bonds. Okay, so this is generally the rule for Lewis structures. they are sharing electrons instead of completely gain or lose the electrons. Okay, so let's take a break. Hey guys. Okay, so here is talk about the Lewis structures for the molecular compound. And just to let you know, the Lewis structure for molecular compound is more complicated. So that's why here we're going to talk about how to write the Lewis structure for molecular compound. How to write a Lewis structure for molecular compound? Well, so if you're one of the example, the CH4. CH4 is a methane. It's called a methane. So if we have this compound, how to write the Lewis structure? First, you need to identify, okay, which one is the central atom, which one is the side atoms. Central atom means the one has only just one. If we only have one atom over here, and this is the central atom. The one has the multiple numbers. The elements, the atoms has the multiple numbers. Those are called a side atom. Okay, so first you need to identify which one is the central atom, which one is the side atom. And then when you write the structure, you're gonna put the central atom in the middle. Okay, you put the central atom in the middle and put the side atoms on the side. So this is a methane. Okay. Then the next part, you need to count how many Lewis structure or how many valence electrons do we have for the whole molecule. How many valence electrons do we have for this? How to count? You just need to look at the valence electron for each of the elements. Carbon is in a 4A group. So carbon has 4 valence electrons. Hydrogen is in the 1A group. So hydrogen has 1 valence electrons. But how many hydrogen? I have 4 hydrogen. So you're gonna time 4. So totally it's 4 plus 4 of 1. Then totally we have 8 valence electron for methane. Okay. So if we have 8 valence electron, in another word, we are going to have 8 valence electron, 8 dots surrounded for this molecule. So we can only assign 8 dots, not 10, not 6, but only 8. Okay. So is there any rule for assigning 8 dots? Yes, of course. Before we assign the dots, we need to make sure. Okay, so this is a structure that we are writing over here. Each of the carbon and the hydrogen, between each of the atoms, you're going to have a shared electrons, right? At least you're going to have a 1 pair shared electrons over there. Otherwise, how come the carbon and hydrogen will connect to each other, right? We talk about their shared electrons and connect them to each other. So you're going to assign the shared electrons first. Okay, you need to assign the shared electrons first. So if you're then you need to see, is there any more dots? No, we already assigned 8. If there's more dots, then we need to assign more. But here we only have 8 electrons, and you already assigned 8. Then boom, we're done. But before we finish this, we need to double check. There's a rule. It's called the octet rule. Octet rule, which means, and there's another one, it's called a duet. Duet rule means it's only for hydrogen and helium, because those two elements, they only need 2 dots. Okay, around those only need 2 dots. They only need 2 dots to be stable. Okay, because helium and hydrogen, they are in the just 1s and 1s or subshell. The 1s only have 2 electrons can be assigned. So they just need 2 electrons, then will be stable. For the rest of us, they need 8 electrons. Octet means 8. So they need 8 electrons to be stable, to be full. So you need to double check, okay, is this Lewis structure we do is all correct? So first, we know we already assigned 8 electrons, and we do have 8 valence electrons. So we put 8. Then you need to double check whether each of the elements follow either the octet or duet. So the hydrogen here, the 2 electrons, the hydrogen follow the duet. This hydrogen also duet. This hydrogen duet. This hydrogen duet, which is good. How about carbon? The carbon also followed duet, because surround the carbon, they have 80 electrons. Boom, everything great. Okay, so this is what happened. So after you're assigned, you have to double check whether all the elements follow the duet or octet. This is the very important part. Okay, so this is for the methane. We can have another examples. Like water. Okay, so again, we need to make sure which one is a central atom, which one is a side atoms. So the central atom obviously is oxygen, because oxygen only have 1. So you put oxygen in the middle, and hydrogen, you're gonna put the hydrogen on the side. And then you're gonna see how many valence electrons for the water. Hydrogen is 1 valence, and we have 2 of them. And the oxygen is in the 6A group, so oxygen has a 6 valence. So totally, we're here still 8 valence electrons. We're still 8 valence electrons. So water totally has 8 valence electrons. So in this case, first we're going to have 2 dots to assign it. Okay, so we're going to have 2 dots to assign this to between the shared elements, and then we are having 4 more to go. Okay, so we only have 4 dots, and we need 4 more to go. Where should we put? Well, again, never put on the hydrogen, because hydrogen only filled for duet, which means hydrogen only need 2 electrons. This hydrogen already have the 2 electrons, so you don't have to assign more dots on the hydrogen. Do you understand? Okay, very, very important parts. So the only parts you can assign, that's gonna be on oxygen parts, right? Yeah, so you just need to make this oxygen as an octet first. Okay, so make the oxygen as an octet first. And then we're done, because we only have 80 electrons to assign. Then we're having the Lewis structure like this. And I forgot to mention in the previous part, once you're done, you double check everything follow octet and do it. Then you need to get rid of those shared electrons and then making single bonds over here. Okay, since we only have 1 shared electrons, so make it as a single bonds. So this is the Lewis structure for water. Okay, so this is the Lewis structure for water. We can do one more, like a CO. Carbon, Monoxide. So if you say which one is a central atom, which one is side atoms, both of are one. So it's just one carbon and one oxygen. That's it. Okay. No one counts as a central atom. No one counts as side atoms, but just the two. We only have two over here. So then you look at how many valence electrons this guy has. Carbon has 4. Oxygen has 6. So totally we have 10 valence electrons. It is a little bit more complicated. Okay. Then what we're gonna do? You're going to assign the dots. So in this case, if the only have so in this case, we are going to have first you need to have a pair of shared electrons in the middle of those two elements, and then you're going to assign the other dots. Here the rule is we always to assign one of the elements as a octet first. Okay, so if you want to assign the dots, don't assign 2 here, 2 here, 2 here, 2 here. Then in this case, none of them follow the octet. Okay, so if you have extra dots, you first make one element octet first, and then if you have extra, and then assign the dots to the other elements. Are you clear? You understand what I'm talking about? Okay, so. So follow this rule. That means we're going to just assign the 6 more dots on the carbon. And in this case, carbon will be octet. Then we don't have to worry about carbon. Since here we have 10 electrons, and then we have 10, so we have 2 more dots to go. So please do not assign the dots like this. Then you say, oh, perfect, everything octet. But did you count how many dots over here? We have 8. Now we have 14 electrons, 14 dots assigned in this here, which is not makes sense, right? We only have 10 electrons, so you can only assign 10 dots over here. But if you just follow the rule to assign 10 dots over here, then something happened. That's because if you double check, only carbon follow the octet. Oxygen is not follow the octet, which means this is not completely correct. This formula is not completely correct because oxygen here only have 4 electrons instead of 8. So you need to try to make something as to make this as 8. So if your things happened like this, what are we gonna do? We're going to moving the lone pairs to the shared electrons. Okay, the lone pairs we have how many lone pairs we have? We have 1, 2, 3, and 4. We have 4 lone pairs to the shared electrons. Which lone pairs are we going to move? Well, some of the students said, can we move over here? This paired electron over here? Well, you can try, but just to let you know, if you move this one, it doesn't work. So originally oxygen has a 4. If you're moving this pair over here, it's still 4, right? So you don't move the one has less dots. Don't move the one has less dots. So to keep those lone pairs, what you need to do is moving this shared electrons to those lone pairs to the shared electrons. So you will see something like that. Well, then you can check, okay, carbon is still 8, but oxygen here, they're from 4 to 6. So they have 2 more. But the point is, this is still not feasible. Then what are we gonna do? What are we gonna do to make the oxygen 8? If one pair doesn't work, then go 2 pairs. Okay, So we can move this to the shared electrons. So you will see something like that. Okay, then you double check, okay, this carbon has 8 electrons. And this oxygen will also has 8 electrons. So now everything follow the octet. That's it. Okay. But here, instead of we have one pair shared electrons, we're having 3 pairs of electrons. So in this case, this carbon and oxygen has the triple bonds instead of single bonds. Okay. And then here is the Lewis structure for CO, for carbon. Are you clear? Okay. So this is for the CO, carbon monoxide. And we can do one more for carbon dioxide. Okay, carbon dioxide. First of all, you need to see, okay, carbon is a central atom, so put it central, and oxygen is side, you put it on the side. And then how many valence electron do we have for carbon dioxide? Oxygen, carbon has 4, and oxygen is 6 valence electron, your time 2. So totally we have 4 plus 12. So totally we have 16 valence electrons for carbon dioxide. Okay, and then we know we have to have shared electrons in the middle first. And then we're going to assign the dots. Here, very, very important. Listen to me carefully, okay? When you assign this has multiple dots, then what are we gonna do? First, to assign 4 on the side atoms first, okay? You're gonna leave the central atoms, do central atom later. So assign all the electrons for the side atoms first, and make sure the side atom will follow the octet. So that means first we have 16 electrons. We're using 4. Now we're going to assign the rest of those electrons. Where we gonna start? We're going to start from the side atoms. So we're going to fill the side atoms as an octet first. So this is a rule, very, very important. Okay, yeah. So now we have 6, 8, 10. Now oxygen on the left side already octet. Now we have 10, 12, 14, and 16. Okay. So now in this case, we already assign all the 16 valence electrons, and each of the side are already full. Please don't add 4 more dots over here. This is not correct, okay? We only have a 16, so this is what happened for the 16. And then if you see 2 oxygen are octet, but for the central atom carbon is not, okay? Yeah, it's not. Then what we're gonna do? We're going to, so in this case, we're short of the dots to making octet. And only in this case, if you're later in the future, if you assign some of the structures and short of the dots, then you need to think about the double bonds or triple bonds, okay? Yeah, so at the beginning, only think about is a single bonds. And then if you're short of dots, then think about the double bonds or triple bonds. So you can have a pair of this. Each of this will be shared to the carbon, okay? Each of this will share to the carbon. Then they're going to become something like this. Then you will see the oxygen octet, the carbon also has octet, and the oxygen on the right side also octet. So you can remove those shared electrons, making a double bonds. then that's it. That's gonna be the Lewis structure for the CO2. That's gonna be the Lewis structure for the CO2. Okay, so let's do one of the practice over here. Please write the Lewis structure for PCl3. Okay, make sure PCl3, okay, phosphor trichloride, PCl3. Okay, first, which one is the central atom? Which one is the side atoms? And then how many valence electrons do we have? And then figure out what is the valence electrons. And then put the shared electrons in each of the middle between each of the elements. And then you're going to assign the dots around the side atoms. Then last parts, you're going to assign the central atom. And then double check which one, whether all of the elements follow the octet or do it. Okay, so let's looking at over here. The phosphor is the central atom, and the chlorine will be the side atoms, which is around the phosphor. Okay, and then let's see how many valence electrons do we have. Phosphor is 5 valence electrons, chlorine is 7 times 3. So totally 21 plus 5, we have 26 valence electrons. In another word, we're going to assign 26 dots. Okay, so first we already have the 6 dots already in the shared electrons. Okay, and then we're going to assign the rest of the 20s. So we talk about you're going to assign the dots around the side atoms first to make the side atom octet first. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we assign all the side atoms and make everything as octet. Then we have a 22, right? Or 24. So we have a 2 more dots to go, and those 2 more dots have to be in the central atoms. Okay, have to be in the central atoms. So in this case, you will see, okay, chlorine octet, 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 and phosphor also follow the octet. That makes sense, right? Okay, so then you're going to move the shared electrons to making a single bond because they only have 1 shared electrons. So that is the Lewis structure for PCl3. And this guy has 3 bonds and 1 lone pairs for the central atoms. Okay, 3 bonds and 1 lone pairs for the central atoms. And for each of chlorine, they have 1 bond and 3 lone pairs. That's it. Are you clear? Okay. So for the one has the charge, the polyatomic ion generally is doing the same thing. Polyatomic ion, they are doing the same thing. For example, NO3 minus. Okay, this is the nitrate ion. How to write the Lewis structure for nitrate ion? You're doing the same thing. You're going to figure out, okay, what is the valence electrons for nitrate ion? Nitrogen has a 5, oxygen has a 6, times 3. This number is 5 plus 18, we got 23 valence electrons. But don't forget, look at here. What is this? This is a charge. Okay, so this guy has 23 valence electrons, and since this guy gained 1 electrons, become a -1 charge. So this charge gonna be including in the valence electron we talked about here. Okay, so 23 plus 1, you got 24 for this case. Okay, so just one more step. You need to count the charge. If this charge is a negative sign, which means it's a gain. If it's a positive sign, means that's a losing electrons. So you need to make sure whether it's a gain or lose. So totally we have 24 valence electrons. So when you draw the Lewis structure, it's doing the same thing. The nitrogen is in the central and the oxygen is on the side. Okay, nitrogen in the central, oxygen on the side. And then we have those shared electrons over here. And then we're going to assign the dots. But when we assign the dots, we're going to start with the side. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, when we assign the 24 dots, we realize, okay, each of the oxygen follow the octet, but the central atom nitrogen only has 6 electrons. Okay, it's not follow the octet rule, which means we need to have a double bonds. Okay, so we talk about when we short of the electrons, then we're going to have a double bonds. So where we should go? Well, it really doesn't matter in this case. So you can either using 1 lone pairs on the left side, or using 1 lone pairs on the right side, or using lone pairs on the left in the bottom. It really doesn't matter. Just choose one. So we choose this one to be shared over here. Then you will see it becomes something like that. So this all then you double check oxygen, each of those oxygen still octet, and the central atom become 8 electrons too. Okay, so then what are you gonna do? You're going to remove the shared electrons, and you draw a structure like this is double bonds, this is single bonds, this is single bonds. And don't forget, we're having one of the bracket and put the negative charge up here. Then this is gonna be the Lewis structure for nitrate. Well, you said, you think, can I write something like that? Is this good? Yes, of course. Why not? Okay. And is this good? Yes, this is also good. Okay, so you don't worry about which one they are choosing. Each of this is good. So don't worry about which one you're writing for the Lewis structure for the carbonate, for the nitrite. Are you with me? Okay, yeah. Okay, so next part is talk about some exceptions. Well, when you draw the Lewis structure, of course we're having some exceptions. Okay, for example, some of the exception, the BF3, so boron trifluoride. The boron trifluoride, we're going to the Lewis structure we draw for this will be something like that. This is the boron trifluoride. So you will see all the side atoms are all octet, but the central atom only have 6 valence electrons. They only have 6 valence electrons in the middle instead of 8. So this is has a less electrons than the normal things. Okay, yeah. So this guy has less central atoms. But some of the cases, most of the cases you have extra dots in the middle. You have extra dots in the middle. For example, the PCl5. Okay, we just draw the PCl4, PCl3. So here's the PCl5. PCl5, if you're looking at here, the phosphor, and you're going to have a 5 of the chlorine around it. Then you're going to have a 5 shared dots around it. In this case, it's already more than 8 for the central atoms. That makes sense, right? And if you see this guy has 5 plus 7 times 5, you totally have 40 electrons. So already have a 10, and then we putting on the side atoms. You will see when we fill all the side atoms as 8 electrons, they are 40. So that's going to be the Lewis structure for phosphor for the PCl5. So the central phosphor has 5 bonds instead of 4 bonds. We know 4 bonds is 80 electrons. 5 bonds here is 10 electrons over here. So this guy is already more than 8. Okay, this is also exceptions. Okay, but just to let her know, side atoms never be exceptions. The side atoms always has 8 electrons, always has octet. If it's hydrogen, always follow duet. But central atoms could have a less, could have a more. Okay, so if you have some exceptions, then the exception must belong to the central atoms. The exception must belong to the central atoms. Another example is XeF4, xenon xenon tetrafluoride. Okay, xenon tetrafluoride. So if you look at here, xenon is noble gas. Okay, so this guy valence electrons 8 plus 7 times 4, you totally have 28, 36. So xenon in the middle and the fluoride on the side. Okay, and then we're going to have a shared electrons in the middle, of course, and then we're going to assign the dots. So here we have 36, so already have 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So once we assign 80 electrons around the fluorine, we only have assigned 32, which means we have 4 more electrons to go. Okay, where the dots should go, just let you know, the electrons should belong to the central atoms. Okay, the electron should be the central atoms. And another thing is, I would like to see, other than assign like a metal, the single elements, we talk about when you're assigned a single elements, you're gonna assign one single dots on each side first, unless you have more, right? That's for the single elements. But for the compound, we always assign coupled electrons, paired electrons. Because, I mean, when they combine a compound, everything should be paired. Now, all of those electrons should be already paired. Okay, so you have 4 more electrons to go, which means we have 2 lone pairs need to assign to the xenon. So you're going to assign 1 pairs over here and another pairs over here. So in this case, you will see xenon, this guy has 4 single bonds and also has 2 more lone pairs. So that's going to be the Lewis structure for xenon. It's pretty complicated. Yeah, I know it's pretty complicated, but that's going to be the Lewis structure for xenon trifluoride, tetrafluoride. Okay, so this is generally is how we write Lewis structure. This is how we write the Lewis structures. Any questions? Okay, so the one more thing that's coupled with it, I mean, one more thing to couple with it is called a Fulmore charge. Fulmore charge. The Fulmore charge, it generally is helping you to, the Fulmore charge is not try to figure out what is the charge for this compound. It's try to helping you to figure out which formula could be the correct formulas, which one is not correct. For example, we talk about the BF. And if you're based on the rule for the Lewis structures, you will see this. So boron, the boron, for the valence electron, this guy has 3 valence electrons for boron plus 7 times 3. Totally, we have 24 valence electrons. Okay, which means we need to assign 24 dots. If you're looking at this guy, they do have a 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 16,
18, 20, 22, 24. So this guy do have a 24. If you're looking at this one, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this guy also has 24. Then the point is, which one would be the correct formers? You cannot say everyone is correct, right? Which one is correct? And this is where the formal charge is coming out. Okay, so the formal charge is helping you to figure out which one will be the correct formers. Okay, to solve the formal charge, they have equations. The formal charge will be equal to the valence electrons for the single atom and subtract the sum number of bond plus number of electrons not in bond. Okay, so this is how you count the formal charge. Valence electrons, total valence electrons, subtract the sum number of bond plus number of electron not in bond. Okay, what does that mean? You can look at it over here. Each of those elements shows in the compound will have a formal charge, like this fluorine. The fluorine valence electron for this fluorine is 7, right? As long as the valence electron for fluorine is 7, then you subtract the sum of the number of bonds. This fluorine only have 1 bond, so just 1, plus number of electrons not in bond. We have 6 electrons not in bond. So totally it's a 6. So 7 minus 7, that's give you 0. So the formal charge for this fluorine is 0. Okay. And if you're looking at this, it's doing the same thing. Valence electrons for fluorine is 7 minus how many bonds this fluorine have? This has 1. Plus how many dots? 6. So this guy is still 0. So the formal charge for this fluorine is 0. The formal charge for this, then you will see 7 subtract how many bonds? 2 bonds. Plus how many dots? 4 dots. So 7 minus 6, it becomes plus 1. So this guy formal charge become plus 1 instead of 0. And if you look at this boron, formal charge, the valence electron 3 subtract how many bonds? 1, 2, 3, 4. We have 4 bonds over here. How many electrons around it? No electrons, so plus 0. Then 3 minus 4 give you minus 1. Now we calculate the formal charge for this guy. This 2 has 0. This one is plus 1. This one is negative 1. Okay, so give you the formal charge. Then let's looking at this one. So this fluorine exactly just like this. So the formal charge will be the same. Just a 7 minus 1 plus 6. Totally you have 0. And those 2 fluorine is the same thing. So this is also 0. This is also 0. Then let's looking at the boron. They have a 3 minus 3 bonds plus 0 electrons. That's going to be also 0. So if you're looking at the formal charge for this guy, everything is 0. But this guy, 1 is positive 1, 1 is negative 1. So the conclusion is the one has more zeros for the formal charge. That's going to be the better Lewis structures. Okay, the one has more zero formal charge. The better will be they will be the better Lewis structures. Are you clear? Okay, so you can turn the page for the study guide 21. Turn the page, study guide 21. So you can based on the formal charge to figure out question number 6. Question number 6. Okay, to figure out which one will be the best formula for this compound? Which one will be the best Lewis structure for this compound? Question, page 21. Page 21, question 6. Please, if you have some time, please work on the study guide. Okay, please work on the study guide. Okay, based on the formula to figure out the formal charge, to calculate the formal charge. Okay, so let's go review for this question. Here we have two different formulas. Okay, so we can, based on the formal charge, to figure out which one is correct. So if you're looking at this one, this oxygen will be 6 valence electrons, subtract how many bonds? We have 1 bonds plus how many dots? 6. So this is a -1. Hydrogen here, that's gonna be just 1 subtract 1 bonds plus no electrons, that's 0. This one is a 6 subtract 2 bonds.
plus 6 dots, 4 dots, that's a 0. Nitrogen over here, that's gonna be 5, subtract 4 bonds plus 0 electrons, that's plus 1. So we have a 0, 0, minus 1, plus 1. But if you look at it here, the hydrogen here is 0, 1 minus 1 plus 0. So this is a 0.
Oh, yeah. This is a 6 minus 2 plus 4, that's still 0. This oxygen is still 6 minus 2 plus 4, that's 0. This nitrogen is a 5 minus 3 plus 2 equal to 0. Okay, yeah, so that's why this guy is better. Okay, this guy is better. So I'm not sure whether you're making a summary over here. Did you see that? So in this case, oxygen, you see, this is oxygen, Lewis structure, right? They have a 2 electrons are single. In another word, oxygen, the best way for oxygen is to have a two kind of bonds, either 2 single bonds. The best for oxygen either is 2 single bonds, or they have 1 double bonds associated with. So this is the best for oxygen. You see, 1 is here, 1 is here. This is best for oxygen. Does it make sense, right? And if you're looking at for the hydrogen, hydrogen always gonna have a single bonds. That's it, because this guy only have 1 electrons shows over here. They just need 1 electrons, so just need 1 pairs. So they always has a single. And if you're looking at for the nitrogen, this is the nitrogen, and they are having 3 unpaired electrons. So the better for nitrogen has some of the options for nitrogen. Either nitrogen can have 3 single bonds, or they can have 1 double bonds, 1 single bonds, or they are just having 1 triple bonds for nitrogen. Do you think that makes sense, right? So all of those are having the 0 for their formal charge, right? This guy has a 5 minus 3 bonds plus 2, that equal to 0. This is also 5 minus 3 bonds plus 2 is equal to 0. This is the same thing. Okay, so those are the best choice. If you want to choose which one is a good formulas, then you can also from there, then you can figure out which one will be the best formulas. Make sense? Okay, yeah. All right, so today my plan is doing the study guide. Okay, yeah, we are learning the unit 4, but we never do the practice. Okay, I really want you to do the practice, very important. Okay, so we're going to do the practice, the pink sheet. Okay, and on next class, we're going to review the unit 2 exam, and in the last class, we're going to we probably will just yeah, we will have a little bit of lectures, and then we're going to review the exam 3, and then we're going to have in the lab time, we're going to do the practice, the final practice, the ACS practice exam. Okay, yeah. Well, this so this is our plan. This is our plan. Okay. So I'm going to assign some of the practice for you. Okay, so this is what we are going to do the practice. Looks like it's a lot, but actually each of those questions is really short. And if you have any questions, please let me know. Yeah. No,
There's a school site. I want to take a little bit.
yeah, you definitely can have a group together.
No, it's just. That was great. What about it is not here to. What's that? He's right. Because you don't know what you're. Was not on 3D, it is from start right to move, it is not for one. So many things that really long we should just for shortcut and stuff. You're gonna go as one of the normal gas. You're out. It takes oh no, hey, every time you guys think about the last. I know, pretty question. Yeah, just it's too obvious. In class. Yeah. Because it's just like if we wrote, but the NR just stands for. Oh, it's more or less those. So. Then we go to the classroom. Stop looking for a reason. What are you talking about? 4S2, 3. That's true, but why is it 2? That's the, I don't know if that's on purpose or.
Very good one.
Okay, so first of all, let's.
No, that's right. It's one now. I lost. Yeah, well, this one's wrong with this. So like. That's what's wrong. They are all. 3. Well, I picked some points wrong. Yeah, that's what I'm saying. It's on what is it? Or Washington. It's one on. Says, doesn't all right? We just had choice.